All right, thank you, Lenora. So yes, I'll be talking about LIFE paper 10. This is indeed the talk I already gave, so most of these slides are not new. We'll be talking about what LIFE could do if it gets to fly tomorrow with the exoplanets that we know so far. And we already know a few of them. We know a lot of them which transit. We know quite about 1,000 of them which have been discovered in radial velocity. These are generally rather nearby exoplanets below closer than 100 parsecs, many of them at around 20, 30 parsecs. Many of these, as you can see in these plots, are in rather temperate orbits, about 1 AU, these type of orbits that are interesting to get exoplanets for atmospheric characterization. But as long as we discover them in radial velocity, we cannot say anything about the atmosphere of these planets. So we really need direct imaging to characterize all this population of non-transiting exoplanets. And also, we might discuss later that also quite a few of the transiting exoplanets would benefit from LIFE having a look at them, because we know that transit will be probing mostly the very upper layers of the atmosphere. So it'd be great to have this combination also with direct imaging measurements. And direct imaging is it's exciting for a lot of different people. We have this Astro 2020 Decadal Survey saying direct imaging is the way to go for the coming decades. We have this ESA YES 2050 report saying that ESA should push for the characterization of temperate exoplanets in thermal emission. And in particular, in this ESA report, they recommend the community to do a bit of a feasibility study on whether direct imaging mission observing in the mid-infrared, so not live, but probably live, could characterize a reasonable number of temperate exoplanets. They say 10. It is not written in stone, but it gives us a reference. And also whether we could characterize also exoplanets with varying size and insolation, meaning we get to really get a glimpse on the exoplanet diversity and try to really understand what are the conditions that made Earth unique or not, which is a rather lingering question, given that we had this TPF C and TPFI and also this Darwin mission already in the 90s proposed to actually pursue these same science goals. So actually, this dates from a while ago. This dates from a time at which we knew no exoplanets out there. Obviously, we knew no Earth-like exoplanet. Now this has changed quite a bit, and so this is also why we produced this paper to have a look at how this picture has changed since then. The idea to get these old TPFC and TPFI or Darwin, and right now this Habitable Worlds and LIFE complementary approach is based on the fact that visible and mid-infrared will be probing very different properties of the planet or planetary atmosphere. We will have Roman and Habitable Worlds exploring quite thoroughly the visible and the near infrared. Will be sensitive to quite a few molecular species in the atmosphere. I'll go back to that later, but we'll also be measuring clouds in the atmosphere. That's great, but as we'll discuss later, that also will trigger quite a bit of degeneracies in the atmospheric retrievals. We then have this mid-infrared wavelength range where we have all these potential biosignatures with very interesting absorption bands, and also these mid-infrared where we're not sensitive to the cloud properties of the planet, so we can really get the temperature pressure profile and also get an idea of the planet radius. So we'll really want to have both type of measurements, both wavelength range available at some point in the 2040s or 2050s. So we have all this timeline of the Roman Space Telescope as a technology demonstrator for habitable worlds, and also this LIFE proposal more on the European side. We want to check what is the population of planets that they will detect, and we have two ways of doing this. First of them is by means of yield predictions, by means of a simulated population of exoplanets around a given catalog of stars, and this was done in paper 1, for instance, which is get the planet occurrence rates from Kepler, for instance, and then couple that with LifeSim to get a prediction of which type of exoplanets are we sensitive to. Of course, planet occurrence rates have also some drawbacks in the sense that observational biases are affecting, in particular, long-period exoplanets. But this already gave us some numbers, which is an interesting approach, and it's also an interesting approach to compare with this second one based on the set of known exoplanets, which is the approach that we took here. We got all this population of known exoplanets. We basically did download the NASA Exoplanet Archive database, and we ran on it previous statistical methodology to just run thousands of orbital simulations for each known exoplanet by varying all these relevant orbital and planetary parameters. And at the end, we get an output catalog of planets when we apply a given detectability condition. For that, we will be coupling this code with LifeSim, as I'll describe in a second. Basically, we just have thousands of orbits. Each one is divided in about 360 orbital positions, at which we compare the angular separation of the planet and the brightness of the planet with the sensitivity requirements of the instrument. For a reflected light telescope, it is quite a simple approach, which is compute what would be the reflected light that the planet would send to the observer. We will compare the inner working angle and the outer working angle, and we will check whether the planet is within this operating range, and we will say whether that planet is at an accessible position or not. And we will repeat this, as I said, for thousands of orbital realizations for each exoplanet. For life, we did a bit more of it was a bit more complicated because we have LifeSim, which is great. We can get to simulate quite a bit more reasonably and physically accurate all the performance of the instrument, which is something we did not have for Habitable Worlds at the moment. So we just get the equilibrium temperature of the planet, and we compute the emission, the thermal emission of the planet, and run LifeSim to check if we would get a signal-to-noise ratio of 7 in less than 100 hours of integration. If so, we say that the planet is detectable. So with LifeSim, we kind of account for a bit more noise sources than what we did for Habitable Worlds. At the end, with one approach or the other, this is what we end up with. This is the list of potential targets for life here in green and Habitable Worlds here in blue, compared to the whole population of known exoplanets within 20 parsecs, which are all these gray dots and histograms. And here in these horizontal lines, you get the mass of Neptune in blue, the Earth in green, and Mars in red, just for reference. And then we can see that actually life is performing really well in this range of low mass exoplanets, close to the mass of the Earth and also close to the mass of Neptune, while Habitable Worlds is mostly sensitive to the currently known long period massive exoplanets, and this is due to the observational biases that we have right now. Most of the known exoplanets that we have discovered on long period orbits are generally very massive, and so Habitable Worlds will struggle a little bit with the inner working angle, for instance, when observing low mass planets around M stars at temperate orbits, because they will be orbiting too close to the star to be resolved with the inner working angle. So this is already great news. Life can do or could detect most of the exoplanets that we know so far within 20 parsecs. We then did some studies on what are the common targets for both missions, what are the targets that overlap and are both detectable with life and also accessible in reflected light with Habitable Worlds. And we have a few of them. As I said, we don't have that many planets in the mass regime of the Earth or Venus. We have mostly Neptune-like planets and some super Earths or mini Neptunes like the Tau Ceti planets, some of which orbit actually in the habitable zone. So some of these are interesting targets, but we will not reach to the Earth-like regime with the set of exoplanets that we have discovered so far. This is not surprising actually, but what we can see is that we already have quite a few common targets. About, I think it was about 60 or maybe 50 of them. So not bad. This list will just keep increasing with long baseline transit and radial velocity campaigns. So we'll be filling all these gaps in the coming years. But again, when we have a look at the exoplanets that are only detectable with life and not with habitable worlds, well, this changes. We have a lot of very low mass exoplanets, quite a few of them in the Earth-like regime potentially, and we also have a lot of them with equilibrium temperatures close to that of the Earth. So that is great news. Life is quite sensitive to the known population of rocky exoplanets. That means we will be performing very well in observing low mass exoplanets at temperate orbits around M stars, while also doing great for temperate exoplanets around G-type stars. So life will be able to do both exoplanet regimes, something that habitable worlds will not be able to do. M stars will generally be left out of the habitable worlds target list. Again, we already have quite a few interesting targets. We have about 38 of them, which are detectable by life and which orbit in the habitable zone of their system. So you have here a huge list of them. I mean, I don't want you to pay attention to all of these targets, but what you can see already is that green dots, which are proportional to the mass of the planet, means the planet is detectable with life. These white star markers indicate that this planet would also be observable with habitable worlds in reflected starlight. And these gray dots in here, black dots in here means that the planet is not doable with life. Well, we get a few of them. I mean, we can pay attention to different things that we might be interested on. For instance, we have quite a few multi-planet systems. I think this is great. This is great news to be able to detect several exoplanets in the same systems at different levels of insolation. We also get quite a few systems in which we have planets both inside and outside of the habitable zone. For instance, in here, and if we move to the next slide, mostly all these M-star planets are observable with life, but you can see that the habitable zone planets are not doable with habitable worlds, meaning that some very cool targets such as Proxima Cn-b, the T-Garden star planets, and some more are only doable with life and not accessible to habitable worlds. I think these are all quite interesting targets, and we can discuss maybe later if some of the science projects that we have around characterizing the atmospheres of habitable zone exoplanets with life can be potentially applied to some of these systems. What else? Let me say that we really need to push for this dual approach in which we have both direct imaging in reflected light and direct imaging in thermal emission. We really need both wavelength ranges to get the most out of these observations. Again, as I said, reflected light observations in the optical and near infrared will be very sensitive to cloud properties in the planet. We could potentially get to detect also the ocean glint, such as we have seen for the Earth or for some solar system bodies such as Titan. We could potentially be sensitive to the vegetation red edge. So it is not about wavelength range for biosignatures, but again, cloud properties will be hindering quite a few of these conclusions at some point. Life, on the other hand, could get a very good estimate of the planet radius. Even if the planet is not transiting, we will be able to measure the pressure temperature profile, and we will be sensitive to molecules that are very relevant for studying biosignatures. But if we combine both measurements, we will be actually be able to get more than the sum of each individual measurement. We'll be able to break this radius albedo degeneracy. We'll be able to derive the wavelength-dependent albedo that gives us an idea on the energy budget of the planet. We will potentially be able to study whether a greenhouse effect is present on that atmosphere or not. So again, we would ideally want to have both mid-infrared and reflected light observations. So the summary of the work is, well, we found that if we launch the instrument tomorrow, we'll already have 38 habitable zone targets to play with, so not bad. We're restricted to planets within 20 parsecs. We can think about moving this study even further out, and some preliminary work that we did shows that there are still planets detectable at, say, 30 to 40 parsecs. Again, current observational biases are strong, obviously, and they are preventing us to detect an Earth-like planet around a Sun-like star. This will arrive at some point in the coming years. But again, just with that, we have about 50 planets that are both targets for life and habitable worlds to get these multi-instrument observations, ideally. And again, we need those because combining reflected light and thermal emission will be key to actually unveil the atmosphere of these planets and break all the parameter degeneracies that will be present in atmospheric retrievals with one single spectral range and the other single spectral regime. So it is great that we already have some common targets. This list will keep increasing, and then we could wonder what could we do at LIFE internally, so to say, with this list of potential targets. What of the as we talked at the meeting in Berlin, what are the golden targets that we could advertise for LIFE? What are the unique targets that LIFE will be able to characterize and not other instrument? That is something that we might want to think about. So with that, I'll stop here. I'll take questions if any. Thank you.